All right, this is for physics CP, debrief on the answers for the Unit 4E homework problems set. It leads off with number one. What is the kinetic energy of a 3 kilogram object moving at 4 meters per second? Of course, all that is to just one sig fig, which doesn't make it very precise. So let's at least calculate our answers out to 2 or 3 sig figs as we develop our answer. Kinetic energy formula is 1/2 times the mass times the velocity squared. So in this situation, it's going to be 1/2 times 3 kilograms times 4 meters per second quantity squared. 4 squared is 16, and 1.5 times 16 would be 24. So the answer is 24 joules. We'll do it to 2 sig figs, even though all the data is only to 1 sig fig. Number two, a 4 kilogram object possesses 18 joules of kinetic energy. What is its velocity? Actually, we can't tell what its velocity is. Velocity is speed with direction, and there's no information that tells us what direction it's going. So the best we can do in this physics problem is calculate its speed. The formula is kinetic energy is 1/2 times mass times velocity squared. Okay, well, when we work backwards, we can't get the velocity, we can only get the speed. And this is the one unknown that we're solving for. Rearranging this equation, we multiply both sides by 2, divide both sides by the mass, and then take the square root of both sides, and that will give us the speed at last. Beep, beep, beep. I get a speed of 3 meters per second with no known direction, so I can't tell you what the velocity is. And those numbers were 2 times 18 joules divided by 4 kilograms square root. In other words, 1/2 of 9, and the square root of 9 is 3. Number 3, an object has 90,000 joules of kinetic energy. And again, that's really just one sig fig here. And is moving at 12 meters per second. What is the object's mass? The formula is kinetic energy is 1/2 times mass times velocity squared. This time we want to rearrange the equation to solve for the mass. So I multiply both sides by 2, divide both sides by the velocity squared, and that will leave me with the mass. So 2 times 90,000 joules divided by 12 meters per second squared and I get a mass of 1,250 kilograms. That's to 3 sig figs. If you want to make it only 2, you'd have to round this up to 1,300 kilograms if you want to express it to only 2 sig figs, even though the original data is only good to 1 sig fig. Number 4, part A. A 40 kilogram box is placed on a 2 meter tall shelf. What is the gravitational potential energy? UG. The gravitational potential energy is m times g times h, where the zero height is arbitrary. We'll take the zero height to be 2 meters below this tall shelf. In that situation, 40 kilograms times acceleration due to gravity, we'll use 9.80 meters per second squared, times the height, we'll use 2.0 meters, and the calculator says 784 joules. If you want that to 2 sig figs, you would round that down to 780 joules. 2 or 3 sig figs are what I'm asking you to do. Next page, problem 4, part B. If the box falls off the shelf, what is its kinetic energy as it strikes the ground? Well, all the energy it has at the beginning of the problem is equal to all the energy it has at the end of the problem. And at the beginning of the problem, all the energy is in the form of gravitational potential energy. And at the end of the problem, all the energy is in the form of kinetic energy. So this is a thinking question, and the answer is the kinetic energy it has as it strikes the ground will be the same as the answer to part A, 784 joules or 780 joules if you want to go to 2 instead of 3 sig figs. Part C. What is the velocity of the box immediately before it strikes the ground? Now this time we can actually calculate the velocity because it's common sense whether the box is going up, which is a positive velocity, or down, which is a negative velocity at the moment it strikes the ground. And therefore, we will take this kinetic energy and rearrange the formula to solve for its impact velocity by multiplying both sides by 2, dividing both sides by the mass, taking the square root of both sides to get the velocity at last, the square root of 2 times 784, I'll leave it that way, divided by 40 kilograms, yields a speed of 6.26 meters per second, but this time we can actually calculate the velocity. So the final velocity is going to be down, so negative 6.26 meters per second, or negative 6.3 meters per second. Yes, you could have solved for this answer using the kinematic equations of motion with constant acceleration, but we want you to practice using energy methods for solving these problems. Problem 5, part A. A 1.5 kilogram ball is thrown upward with a velocity of 6 meters per second. Part A. What is the kinetic energy of the ball as it is thrown upwards? At the moment it leaves your hand, which is the only time when we know its kinetic energy. So just plugging in the values, 1/2 times 1.5 kilograms times 6 meters per second quantity squared, and the calculator reports that is a value of 27 joules. Part B, what is the gravitational potential energy of the ball when it reaches its highest point? At highest point, V equals 0. It stops going up. So all KE, kinetic energy, is, that should be transformed into UG, gravitational potential energy. 3 dots like that in math class means therefore gravitational potential energy equals 27 joules. Part C, to what height above the thrower's hand will the ball rise? Using energy methods, we're taking the formula for gravitational potential energy and we're rearranging the equation to solve for height. Height would be the gravitational potential energy divided by the mass divided by the acceleration due to gravity. Plugging in the numbers, this would be 27 divided by 9.8 divided by 1.5. Beep, beep, beep. I get a height of 1.8 to 2 sig figs meters. And yes, you could have gotten that using the kinematic equations of motion, but again, we want you to practice using energy methods. Number 6, a 2-kilogram watermelon is dropped from a 4-meter tall roof. How fast will the watermelon be moving as it strikes the ground below? Yes, you can use the kinematic equations of motion. However, we're going to use energy methods. So, assuming that it is dropped from rest, that tells us its initial kinetic energy is 0, and its total energy is strictly in the form of gravitational potential energy, which for a 2-kilogram watermelon on planet Earth at a height of 4 meters corresponds to 78.4 joules, the same number we had in our ostrich egg problem. It was a 2-kilogram ostrich egg from a 4-meter tall roof, you might recall. And so therefore, when it strikes the ground, all of that gravitational potential energy is transformed into kinetic energy as it strikes the ground. That is a value of 78.4 joules is 1/2 times mass times velocity squared. We can rearrange this equation to calculate its impact speed. And fast, by the way, is a scalar question, speed, not velocity. Solving for the kinetic energy, that's going to be 2 times the solving for the velocity, 2 times the kinetic energy divided by the mass, take the square root, you'll have the velocity or speed at last, and the square root of 2 times 78.4 divided by 2 is 8.85 meters per second, or 8.9 meters per second if you want to do it to 2 sig figs instead of 3. Number 7, to what height will a 250-gram soccer ball rise if it is kicked directly upward at 8 meters per second? Yes, you can use the kinematic equations of motion with constant acceleration as a free fall problem for basically this entire worksheet. However, you should be practicing using energy methods. In that situation, we calculate its initial kinetic energy by the formula 1/2 times mass times velocity squared, 1/2 times grams. You should know that there are 1,000 grams in 1 kilogram, so 250 grams is 0.250 kilograms. 8 meters per second squared is 64 meters squared per second squared. Half of that and a quarter of that will give us our answer. Or if you like, use the calculator. 1/2 times 0.25 times 8 squared, and we get 8.0 joules of kinetic energy initially. Well, since it's going straight up, all of its initial kinetic energy becomes transformed into its final gravitational potential energy. So, UG, the gravitational potential energy of 8 joules, is the product of the weight of the object, mg, times the height over which it rises. To solve for the height, we divide the gravitational potential energy by mass divided by gravity. 8 divided by 9.8 divided by 0.25 is 3.27 meters, or 3.3 meters if you want to do it to only 2 sig figs.